Before we start this presentation, let's set up a basis of why would we care about fluids? What's the use of it? What's the applications of it? Well, the physics of fluids is the basis of hydraulic engineering, a branch of engineering that is applied in a great many fields. For example, a nuclear engineer might study the fluid flow in the hydraulic system of an aging nuclear reactor, while a medical engineer might study the blood flow in the arteries of an aging patient, Or an environmental engineer might be concerned about the drainage from waste sites or the efficient irrigation of farmlands. A naval engineer might be concerned with the dangers faced by deep-sea diver or with the possibility of a crew escaping from a downed submarine. I can go on forever, but there's a lot of applications of fluid engineering, fluid mechanics, and fluid dynamics. There's a lot of use of it. So let's just go on and start learning about it. Well, before continuing, let's start with the first of all definition, a fluid. Well, a fluid, in contrast to a solid, is a substance that can flow. Fluids conform to the boundaries of any container in which we put them. They do so because a fluid cannot sustain a force that is tangential to its surface. In a more formal language, we can say that fluid is a substance that flows because it cannot withstand a shearing stress. It can, however, exert a force in the direction perpendicular to its surface. We'll later learn this force as pressure, but let's not get ahead of ourselves. Some materials, such as pitch, take a long time to conform to the boundaries of a container, but they do so eventually. Thus, we classify them as fluids as well. So, to classify something as a fluid, we just needed to conform to the boundaries around it and make sure that it flows. Now, if that's the case, can we consider gas as a fluid? Yes, in that case, in that technical definition, we can say that gas is a fluid. And in fact, in later examples, we'll see that gas and liquid work the same way. You can actually change most of the examples from liquid to gas, and it will probably work the same way. You might need to change a bit of volume or whatever, but it'll still work the same way. Thus, we can say that gas is also a fluid. So let's start off with density. To find the density of a fluid at any point, we isolate a small amount of volume we call delta V around that point and measure the mass or delta M of the fluid contained within that element. If that's the case, then the formula for that point for density is this. In theory, the density at any point in a fluid is the limit of this ratio as the volume element delta V at that point is made smaller and smaller. In practice, we assume that a fluid sample is large relative to atomic dimensions, and thus we can call it smooth, with uniform density, of course, rather than lumpy with atoms. This assumption allows us to write the density in terms of the mass M and volume V of the sample, in which case the formula turns into this, because of course it's uniform density. Now, density is a scalar property, so it doesn't have it's scalar basically, but its SI unit is kilogram per cubic meter, and other than that, we can actually see that here are some amounts of densities. For example, styrofoam, ice, water, whole blood. All of these are fluid, by the way. Iron, it means as in fluid iron, by the way, not that solid iron. Solid iron is a lot more different. We're talking about fluids here. Interstellar space, air, which is again air, interstellar space, that's gas, so that's technically fluid. We can say that as well. But you can actually see here in air, the pressure of the air makes a difference in density. And this is because, again, gases can compress. You can actually see that the pressure gets bigger, the density as well gets bigger. That's practically compression. And that's that. Now, other than density, we can also calculate pressure. To calculate it, let a small pressure sensing device be suspended inside a fluid-filled vessel. In this picture right here, the sensor consists of a piston of surface area delta A riding in a close-fitting cylinder and resting against a spring. A readout arrangement allows us to record the amount by which the calibrated spring is compressed by the surrounding fluid, thus indicating the magnitude delta F of the force that acts normal to the piston. We define the pressure on the piston as P equals F per A. The force that's pushing into the area. Now, if the force is uniform, in which at every point of the area, the magnitude of the force is exactly the same or uniform, we can conclude that the pressure is just the whole magnitude force divided by the total surface area. If it's uniform, that is. If it isn't, then you have to calculate it to limits. Other than that, we find by experiment that at a given point in a fluid at rest, the pressure P divided by this formula has the same value no matter how the pressure is oriented. So for example, if this sensor we rotate it, for example, we tilt it a bit to the left or we turn it upside down, it doesn't matter. The pressure is still the same. We can conclude this that pressure is also scalar. And the SI unit of pressure is Newton per square meter, which is given a special name, which is Pascal. In metric countries, however, the pressure gauges are calibrated in kilopascals. The Pascal is related to some other common non-SI pressure units. For example, 1 atm or atmosphere equals 1.01 times 10 to the power of 5 pascals, or 760 torr, or 14.7 pounds per inches squared. But in metric countries, for example, Indonesia, we use Pascal or kilopascals. Now, the atmosphere or ATM is, as the name suggests, the approximate average pressure of the atmosphere at sea level. The torr, or named for Evangelista Torricelli, who invented the mercury barometer in 1674, was formerly called the millimeter of mercury, or mmHg, millimeter mercury. In here, you'll see some pressures, examples of it. For example, center of the sun is 2 times 10 to the power of 16. Or center of the earth, which is less, 4 times 10 to the power of 11. And you can actually see here that the deepest ocean trench, 1.1 times 10 to the power of 8 is the pressure. And all of this is in pascals. And most of this, if you have that much pressure around you, then you're probably dead by now. But other than that, these are the levels of, these are some examples of pressure. Let's continue with calculating pressure at different levels of depth. In this picture, we can shows a tank of water, or other liquid, as long as it's a liquid, open to the atmosphere. Now, as every diver knows, the pressure increases with depth below the air. So for example, the more deep you go, the higher the pressure is. And actually, most divers have a pressure sensor that not exactly, but works the same way as this to calculate how much pressure there currently is around the diver. And that's just a bit of a trivia, but let's continue. Now, but as every mountaineer knows, the pressure decreases with altitude as one ascends into the atmosphere. So you can conclude that the more you go up, the less pressure there is, and the more you go down, the more pressure there is. This is because they are due to fluids that are static or at rest, hydrostatic pressures. Here, we want to find an expression for hydrostatic pressure as a function of depth or altitude. So we're able to calculate the pressure at any levels of depth, if it's hydrostatic, that if it's at rest, not moving. Moving is a lot more different. First of all, let us look first at the increase in pressure with depth below the water's surface. We set up a vertical y-axis in the tank, for example, like this, where this is 0, with its origin at the air, water interface, and the positive direction upward. We next consider a water sample contained in an imaginary right circular cylinder of horizontal base, or face area A, such that y and y2 are the depths below the surface of the upper and lower cylindrical faces, respectively. So we'll just have an imaginary cylinder with y1 being the top area of the cylinder and y2 being the bottom. This is imaginary, by the way, so it's not like an actual cylinder. Now, if we to calculate the amount of force, happening to that imaginary cylinder, there would be 3. First is this downward force. This downward force is due to the water pressure pushing on the top surface. The pressure going down here. So we can call this F1. While the upward force is because of this water here. Is due to the water pressure pushing on the bottom surface. Because of the water here, actually, excuse me. And then other than that, is the gravity. Gravity pulls downward on the sample. From here, we can actually calculate that to calculate pressure at different levels of depth, we use this formula, with G being the gravity and ρ being the density of the fluid. So density and pressure actually have a certain connection, which is this. Now, one of the famous things about fluid mechanics and fluid as a whole is Pascal's principle. Now, consider a case in which an incompressible fluid or a liquid is contained in a tall cylinder, for example, like this. Now, the cylinder is fitted with a piston on which a container of lead shot rests, which is this. Now, the atmosphere, container, and shot exert pressure on the piston and thus on the liquid. So the gravity of the lead shot, the container of it, and the atmosphere around it itself is exerting an amount of force on the piston. And because of that, it exerts some amount of pressure into the liquid. Now, because of that, we can conclude that the pressure, to calculate the pressure of it, is this. The total pressure, that is, which is the pressure of the external source, which is lead shot, container, and the atmosphere, plus the density of the liquid times the gravity and the depth of it. We get this from the last formula, which is this. Which is this. Now, you can see that this is y1 minus y2, right? If we were to put y1 as the start of the liquid and y2 as the bottom of the liquid, or p in this case, or p in this case, we can say that because y1 is 0, as you can see, we'll say that it's just the density of the liquid times the gravity times the height. Now, you'll see that here, that it's negative. Then shouldn't it be in here negative? Well, yes, but that is height. Remember, we're talking about depth. Because it is depth, it actually gets much more pressurized at the bottom. Because of that, it's positive. If you want to talk about the decreasing of pressure, which is height, then you might want to add a negative symbol to that. But we're talking about depth here, which is the reason why we add the amount of pressure to it. Now, let's add some more lead shots. For example, we add more weight onto this whole thing. Because of that, the amount of force should get bigger because of how heavier it gets. Now, since it's incompressible, the amount of pressure would increase. Now, the height, if we were to then calculate the difference of pressure, we'll realize that height doesn't play a role, which is how we'll get this Pascal's principle, which means that the delta, that the difference of pressure it made, it just equals to the amount of pressure the lead shot created. The difference, I mean. It does this part of the formula doesn't play any role in the difference because we only add lead shots to it. Now, this principle actually has a lot of uses to it. One of them is this hydraulic lever. If we were to add a small amount of force to it, then there will be pressure in here. Now remember that liquid is incompressible. Because of this pressure needs to go somewhere to make the whole thing at the same amount of pressure. Because of this, if we were to put a small amount of force in here, that pressure will move here and exert a huge amount of force. So a small input creates a huge output. We can even calculate it using this formula. Now, other than Pascal's principle and measuring at different levels of depth or height, there are a lot of other things that we haven't even talked about. Most of them are Bernoulli's equation, which these two here, and Archimedes' principle. Now, I will not get too technical and deep into these because it will take the video too long and it will be tiring. So I'm going to give a quick rundown to just give you guys a quick summary, basically, of what they are. Now, at the start with Bernoulli's equation. Now, Bernoulli's equation basically states that, states this. Now, this formula actually came from, we can actually change this formula to this. And if you guys remember, this formula is the formula when we want to measure pressure at certain levels of depth. Now, to get to here, we can say that the speed or the velocity of the water or the fluid which is this velocity, is 0, which means that the fluid is at rest. And remember, we can only use this formula if the fluid is at rest. So really, this is just more of a complete equation. And in fact, we can get another equation from here, which is if the the height, which is here, of the two states that we're trying to calculate is the same. For example, 2 or 0. Well, in that case, we can say that we can say this equation, or in other words, the pressure of a fluid, of a moving fluid, and the velocity of that moving fluid must stay the same. If the velocity increases, the pressure must decrease. If the velocity decreases, the pressure must increase. This is basically what this formula is stating. Now, this whole formula actually came from the other formulas that we have talked about, but they just added this kinetic energy. You can actually see it is similar to kinetic energy and potential energy, and this is the pressure. And because again, energy cannot be created nor removed, cannot be created nor destroyed, so the total energy must stay constant. This is basically the Bernoulli's equation. Now, other than that, we have Archimedes' principle. Now, Archimedes' principle states that there is a buoyant force that is happening to an object submerged. It can be fully submerged, or it can only half submerged, as long as it's in water. There is a force that is happening to it due to the pressure of the surrounding water. Now, this pressure, you can actually see these arrows on the top, is have less length than the bottom one. This indicates that the bottom pressure is a lot more. Now, why is it a lot more? Because again, if we measure the pressure at this level and at this level, or at different depth, we'll realize that the deeper you go, the more pressure there is, as have been stated. Because of that, the pressure in here will be more than the pressure on top. And since pressure equals force divided by area, and the area stays the same, the force must be higher. So there should be a higher force down here rather than up here. Now, and imagine this as a hole in the water. Basically, the water cannot go here, which is the reason why there's pressure. Now, let's replace this hole with wood, a lightweight wood, basically. Now, the area is still the same. We've only replaced the hole with lightweight wood that has mass. And when it's lightweight, we know that the force because of the gravity is low. And if it's low enough, the net force would be upward because the buoyant force is higher than the gravitational force. But let's replace this lightweight wood, with really heavy rock or a stone. And since it's heavy, it should have a lot more force of gravity on it going down. And if it's big enough, it can withstand the buoyant force and goes down. This is the reason why some objects actually go up while some objects go down, and it's usually because of density of the object or because of the mass it has. But other than that, it just says that some objects go up, some objects go down when placed in water. And this is because of, again, the pressure surrounding the object. Now, but there's also a really rare one where an object just stays still in the water. This happens when the force of gravity and the buoyant force is actually the same or close enough that the movement of the object and the acceleration is so slow that we see it as floating in the water. This is when both of the forces stay the same. And that is basically Archimedes' principle. And other than that, there's nothing else. There might be more. I might missed some other materials, but this is the best as I can do. I apologize if there's any other mistakes or things that I forgot or things that I say wrong. I'm learning here too as well. Thank you very much for watching. Hope this material helps someone, helps you, or helps your friends. Share this video if you can. Thank you very much.